Okay, in this video we're going to be starting our third module, and we're going to be sort of changing gears here somewhat. So everything that we're going to talk about in this module corresponds to chapter 4 in the text, and we're going to be talking about dynamics in this module. So far we've been interested in kinematics, which was the study of motion without being concerned about the causes of that motion. Now we're going to get involved in what's causing things to move, right? So dynamics considers the forces that affect the motion of moving objects, okay? And so one of the key concepts in dynamics is going to be this idea of forces. And so I think we all intuitively have some idea of what a force is. When people think about forces, generally they think about a push or a pull on some sort of an object, and this is a good place to start. Forces are a vector quantity, so they're going to have magnitude and direction. And like all the other vectors that we talked about, forces can be added up using the same vector tools we were talking about a few videos ago, right? We can talk about the SI units for forces, but before we can talk about the SI units for a force, we need to introduce the concept of mass. And again, mass is another thing that we probably all have a pretty good intuitive understanding of. Mass is just effectively it's a measure of the amount of stuff or matter in an object, right? So the mass just tells us how much stuff is in the object that we're talking about. The SI units for mass are kilograms, and we're going to find that the dimensions of a force are just mass times the dimensions of an acceleration. And so this word dimensions, we're going to talk a little bit more about dimensional analysis in the future, but for now it's basically just leading us to the SI units for a force, and we're going to find that the SI units for a force are this collection of units that we see here. So if we collect them all together, we call 1 kilogram meter per second squared 1 Newton. So a Newton is just a kilogram meter per second squared, and Newtons are the units that we're going to use to talk about the magnitudes of forces. Okay. So as is the case with a lot of other problems that we're going to be working on, when working with forces, it's often useful to start by drawing a diagram, right? And then when we have that diagram, we can then use it to generate a free body diagram, which we're going to talk about in a second here. So let's just imagine, first of all, that we have some sort of an object here. I'll just draw it here. This object, maybe we know what its mass is, some object of mass m, and it has a couple of forces acting on it. Let's say we have a force here and a force here. Let's call this one F1, that's our first force, and this one's F2, our second force, right? And so a free body diagram is going to help us analyze how these forces act on this object. So in a free body diagram, we replace the object with a single point, and then we draw in all the external forces acting on that object. So let's do that in this case here. So for example, if we wanted to turn this into a free body diagram, then what we would end up getting is something like this. So this dot represents our mass, and the forces acting on it are F2 acting in this direction, and F1 acting in this direction, right? And then we won't actually do the algebra here, but just pictorially we can see what's going to happen if we want to add these forces up. So let's say we wanted to get the net force acting on this object. I'm going to always label free body diagrams FBD. Okay, so that's our free body diagram. Then if we wanted to find what the net force was, we would end up finding that our object has a net force, F net equal to F2 plus F1, right? And that would be a vector for sure. Okay, so that's sort of how we would deal with this pictorially. We're going to see how this all sort of applies as we get into some of these examples. But for now, we're going to quickly move on to Newton's 3 laws of motion. And these are going to sort of lead us to a need for these free body diagrams as we get into examples, specifically applying Newton's second law here, which we're going to cover in a second. So Newton's 3 laws of motion sort of form the foundation of dynamics. And let's just get right into them. So Newton's first law, which I'm going to abbreviate as N1 often, this is what's often called the law of inertia, and it just states that a body at rest or in motion remains at rest or in motion at constant velocity unless acted on by a net external force. So that's kind of a mouthful, but we're going to see that really it just represents some pretty intuitive ideas that we can sort of bring to light as we look at Newton's second law here. And Newton's second law is really the only one of these three laws that has a sort of mathematical formulation that can really answer some questions about forces applied to systems, right? And so let's take a look at Newton's second law of motion. So Newton's second law of motion basically just boils down to this seemingly simple equation here, right? F equals ma. And it can be written in this way, or it can be written in its scalar form that we see down here, where we're just talking about the magnitudes of the vectors, where in the first case up here we're talking about vectors, right? So direction and magnitude. So really what is this law doing? This law is just mathematically stating the cause and effect relationship between forces and changes in motion. So forces and changes in acceleration. F is our force, and A is our acceleration, right? And M is what is our mass that we just talked about. And we're going to use this equation a number of different times throughout this course. It's really one of the most important equations in all of physics, and we're going to spend some pretty significant time looking at it and doing a number of different examples with it. Okay, but if we just look at it sort of in this form here, really it's kind of intuitive what it's saying to us. Let's just look at some of the things that we can sort of read from it. If we increase F, we see that A also would have to increase, considering that there's going to be a constant mass, right? Considering that we're not changing mass. But for whatever object, which generally wouldn't change mass, if we increase F, increase the force, then we have an increased acceleration. A change in the direction of our force, so if F starts pointing in a different direction, is going to change the direction of A, right? So as F points in a different direction, then A has to point in that same direction. Increasing M will mean that we require more F to keep the same A, right? So increasing the mass will mean that we require more force to keep the same acceleration. And we can kind of see that just by rearranging. If we just want to isolate A, this just means that A is equal to F over M. And so if we increase M, clearly we have to increase F so that A is the same, right? And so we can keep kind of playing with this equation a number of different ways and find that a lot of the sort of results that come from it are fairly intuitive. And I think my program just crashed again, but I'll just quickly load it up again. So give me one quick second. Where is it? Here we go. Okay, that's unfortunate. We kind of lost some of the earlier stuff that I drew, but I'll come back and draw that again. So as I was saying, some of the stuff, well, the results that are coming from F equals ma from Newton's second law are pretty intuitive, and we can kind of play with them and see that we get a number of different results. Let's now take a look at a specific example of what we can do with this Newton's second law. And this example is interesting because it's going to kind of demonstrate the difference between weight and mass. So in general, well, weight and mass are not the same thing. And this problem is going to sort of show us how they differ, right? So let's start off. We have a box of mass m equals 20 kilograms sitting on the surface of the Earth. What is its weight? Okay, so as we often will, let's start off by looking at a bit of a diagram here. So let's imagine we have just the ground here. We have some box that's intended to be sitting on the ground, and it's a box of mass m. And so what are we going to see as we look at the forces applied to this box? Well, we know there's the force of gravity pulling in this direction, right? and we're going to have, this thing is not accelerating, right? It's sitting on the ground. So the ground is exerting some sort of a force. We call this force a normal force, pushing up on the box, keeping it so that the box isn't accelerating down into the ground, right? So we have some normal force pushing upward on the box, right? And so we could then turn this into a free body diagram, and what we would find is that we have this is our box. We have the normal force pushing upward, and our force of gravity in a downward direction here. Then Newton's second law tells us that that F equals ma, but it also tells us, F here will be our net force, right? So we need F net equal to ma. And what is F net? Well, F net is just the total of all the forces acting on this box, right? So F net is just Fn plus Fg equals ma. And what is the acceleration of this box? Well, it's just sitting on the ground. So a is really 0, which means that Fn plus Fg equals 0, which means that Fn is equal to negative Fg, right? And so what is this sort of telling us? And actually, I should be careful. Maybe instead of doing it like this, let's pick a direction. I'm going to call this our positive y direction. And if we do that, then I'm going to come back, and if you'll allow me to here, I'll just switch these to negatives because we have our normal force acting in the positive direction of our y, and we have our force of gravity acting in the negative direction of y, right? And if we do that, then shifting this over, shifting our Fg over, will give us Fn equals Fg. And Fg, we're going to find, is just equal to the mass times the gravitational acceleration, right? And Fg really, what we often call Fg, is just our weight. And so we're going to see that the weight of this object is just its mass times gravitational acceleration, okay? And so really this is just a sort of trick of notation. We've just relabeled a bunch of things over and over, but in the end what we're saying is that the weight is equal to the mass times g, and g is just our gravitational acceleration back from a couple of chapters ago, right? So we're going to find this equation useful in the future. We're going to see that we use Fg, so the force of gravity, often when we label diagrams like this, but we're also going to use W as a weight, and sometimes we'll just rewrite this as mg, which is just the mass times gravitational acceleration. So we're going to see the three of them used somewhat interchangeably as we do these examples. So let's move on now. We're going to do a little bit more complicated of an example now, so we can really see how to apply Newton's second law to a more complicated system and actually answer some interesting questions about some of these things. So I have an example that I wanted to go over with you guys here. So as I note here, to be able to use Newton's second law, we need to be really good at identifying what the net force is of external forces acting on this object. So we really need to be able to add up all these forces together in such a way and break them up into their different directions in such a way that we can really get at what we're looking for. And we also have to be good at identifying what the system, what the object that these forces are acting on is, okay? And so let's take a look at this example. This is example 4.2 from the text, and it deals with a rocket sled. So we're going to assume that we want to calculate the magnitude of the force exerted by a new rocket that we've developed. Let's say we're engineers, we're building some rockets. So we want to calculate what the magnitude of the force exerted by this rocket is. We're going to call the thrust of the rocket, the force exerted by the rocket, Ft. So that's just going to be the force of thrust. We're going to attach 4 of these rockets to a sled on a track in the following setup. So I'm going to draw the setup here. we have the ground here. We're going to have our rocket sled here. And let's say we have our 4 rockets. 1, 2, 3, 4 rockets attached to the back. And so that's our sled, our setup. So we're going to observe. So let's say we have the setup all set up. We have it sitting on our track here. This is our sled. This is 4 rockets. Okay, so we have it set up like this. We fire off the rockets and we observe that the sled accelerates at 49 meters per second squared. We know the mass of the sled plus rocket system, all that stuff put together, is 2,100 kilograms. And we know that there is a force of friction opposing the sled's motion, which I'll draw in here. We're going to label it like this. This is our force of friction, and it has a magnitude of 650 newtons. Okay. And so the question here is, if we know the mass, and we know the acceleration, and we know the opposing force of friction, what thrust are each of these 4 rockets sort of supplying to the system here? Okay, so the way to do this, first what I would do is I would just draw the forces directly onto our sled, and then we're going to develop a free body diagram. So what's happening? We have the sled accelerating in this direction. We have well, in the vertical direction, we're going to have the weight of the sled pushing down, which is the force of gravity, right? And this is just going to be equal to mg. And I won't write it sort of 3 times every time that I do this. This is just this one time to sort of illustrate what we're doing here. But usually I'll just write mg or w or something, right? In the upward direction here, we're going to have the normal force pushing upward. So the sled isn't digging down into the ground or going upward. So the acceleration is only horizontal here. There's no blasting off of the sled going upward. So our acceleration is not like that, and our acceleration is not like that. It's not digging down into the ground. The sled is accelerating only along the track. Okay. And so what else do we have? We have 4 thrusts here. These are our 4 forces of thrust pushing in that direction, and we've already drawn in our force of friction, which is opposing motion here. Okay, so that's kind of the setup. Now when we want to solve the problem, the first thing that I would do is draw a free body diagram, right? So free body diagram. What do we have going on here? Well, we reduce the sled and rocket system down to a single point. What do we have pushing in each direction? We have the force of friction pushing in that direction. We have 4 times the force of thrust of our rocket. So we have Ft, 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 and Ft in that direction. We have mg in this direction, and we have the normal force in that direction. And maybe just so it's all vectors, I'll just call this w. Okay, so now we want to take a look at each direction individually, right? So let's start off with the vertical direction. Okay, so vertically, what's going on? F net in the y direction, well, that's going to be equal to the normal force in the positive direction minus our weight in the negative direction. This is equal to mass times acceleration, but there is no acceleration in the vertical direction. Again, this sled is not accelerating into the ground or up into the sky, and so this is equal to 0. And what is this telling us? Well, this is telling us that the normal force is equal to the weight. That's great, but that's not going to help us for this problem here. So this vertical direction might be useful in other problems, but in this case, all of our motion and our question about the thrust all involve the horizontal direction. So let's take a look at what's going on horizontally. Okay, so horizontally, what do we have going on? We have F net in the x direction. Well, F net in the x direction is going to be equal to 4 Ft, right? We have 4 of these all being added up here. and then minus lowercase f, right? And this is equal to the mass times the acceleration in the x direction, right? This acceleration over here was in the y direction. This is the acceleration in the x direction. But since we only have the one value of acceleration here, we only have to worry about acceleration in the x direction. So I'm just going to call it ma. And so let's clean this up. What do we end up getting? Well, we end up getting well, I'm going to move this force of friction over to the right hand side, and only keeping two of these terms or two of these values in the equality, we're going to end up with Ft, or 4Ft, equals ma plus f, right? And then quite simply, we're just going to divide through by 4, and we're going to find that Ft is equal to ma over 4 plus f over 4, right? So I have some numbers here written down. Let me see if I can find them. Yes, okay. So this is going to tell us that Ft is equal to the mass, 2,100 kilograms, times the acceleration, 49 meters per second squared, plus our force of friction opposing our motion, which is 650 newtons, over 4. And if we do that calculation, we're going to find that Ft is equal to 26,000 newtons. Okay? So we've solved the problem. Each of these 4 rockets is supplying 26,000 newtons of thrust here. Okay? And so we can kind of ask ourselves a few extra questions here. Let's say, for example, that there was a driver inside this rocket sled thing, and they were pushing back on the steering wheel. Would this push of the driver need to be considered in our calculation? Well, the answer here is no, because the driver would be part of the system. The driver is sitting inside the sled and being accelerated along with the sled and the rockets. They are not applying an external force. They're applying an internal force, and this would not have any effect on our calculation here. Okay? And so as we saw here, we saw an application of Newton's second law, so F equals ma. We know that this can be written also in vector form, which is kind of how we broke up our vectors before. And we also saw that we need to be considering F net, right? So we need to be considering the net force acting on this object, not just one force. But we will find that we can consider each of these forces separately and add them up afterward. But for now, the easiest way to proceed with this is just build your free body diagram, draw in all the forces, find out what the net force is, as I've done in each of these cases, the vertical and horizontal case, and then you're going to find it easier to work with the problem. Okay, so before we finish off this video here, I'm just going to talk quickly about Newton's third law, which is often called the law of symmetry in forces, right? So whenever one body exerts a force on a second body, the first body experiences a force that is equal in magnitude but opposite in direction to the force that it exerted. Okay, and the example to think about here is this one that I've written down here. I think this is one from your textbook, but I don't remember exactly from where it is. But basically, we have a swimmer in a pool, and I'll just draw a little bit here to get a sort of idea of what's going on. We can imagine this is like a wall of the pool, and we have some water here. There's a swimmer underwater. This is going to be a terrible drawing, but I'll do my best. So the swimmer is like coiled up with their legs against the wall, whatever their arms are like out front. And so the swimmer wants to accelerate in this direction. Okay, so the swimmer applies a force on the wall. The swimmer pushes on the wall with a force. We're going to call this force of feet on wall. Right, so that's what the swimmer is actually doing. But the swimmer's intention is to accelerate in the direction of this A that we've drawn in here, right? And so what's going to happen? Well, the wall, The wall pushes back on the swimmer, according to Newton's second law, with a force that's equal in magnitude, so these vectors are meant to be the same length, but opposite in direction. This one points this way and this one points this way. And I've kind of made a mess of this whole thing now, so I'm going to clean it up. But basically what we're going to call this force, this is F. This is the force of the wall on feet. And so what is this? Well, what do we know about this? Well, we know that the magnitude of force of feet on wall is equal to the magnitude of force of wall on feet. And so oftentimes we don't really make much of a distinction here, right? We think of this force that the swimmer is applying on the wall as the thrust that's pushing them forward, but it's important to keep in mind that there is some distinction, right? So if you were asked to tell me what the force of the feet on the wall are, it would be important that you would mention the direction here, right? It is a vector and it does have a direction pointing into the wall. So the swimmer's feet are applying a force into the wall while the wall applies a force outward, accelerating the swimmer, right? That's the force of the wall on the feet. So like if we drew a free body diagram of this, well, what would we have? Well, vertically we would have some force of buoyancy, right? The swimmer is sort of floating in the water, but there's some gravitational force pulling them downward, so they're not accelerating up or down. Those two forces balance out. But since we're only looking at the system of the swimmer themselves, we only need to consider the one force in this direction, and this is the force of wall on feet, right? And so if we looked at this, F equals ma would tell us that, well, there is some F. We have force of wall on feet, and this is going to be equal to mass times acceleration, and this kind of feels weird in this situation because there's going to be some drag from the water, which we're not considering here in this chapter. We will in later chapters, but for now we're not thinking about it. So really this whole example is just to really demonstrate that we want to keep these ideas in mind, right? We want to keep in mind that every time a force is applied by an object, there is an equal magnitude but opposite directional force being applied back on the object applying that force. Okay, we'll leave this here for now and maybe look at some more examples in the next one.